Welcome back, everyone, to the deep dive. Today, we are going to kind of peel back the layers of an operating system that I think a lot of you developers might encounter.
Yeah.
AIX.
Yeah,
AIX,
yeah, yeah.
absolutely. And so today we're going to be focusing on its core, the system architecture, specifically the kernel.
Right.
We're going to kind of give you a developer's eye view into what's going on in that engine room.
Exactly. And for those of you with a good grasp of the technical concepts already, understanding the AIX kernel can really be a game changer.
Yeah.
It gives you such deeper insights into how your applications are actually interacting with the
Whoa.
underlying system,
Right.
which can be so crucial when you're trying to optimize things or debug
Yeah,
effectively.
absolutely. And that is really our mission for this deep dive, is to kind of give you that clear and engaging understanding.
Yeah.
And we've got some pretty dense technical documentation to work with here.
They do.
The kernel extension PDF.pdf and the kernel reftech PDF.pdf documents.
Yeah.
But we're going to try to extract the key concepts.
The most relevant mechanics
Absolutely.
that you're going to encounter in your work as a developer
Right.
without getting too lost in the weeds.
Right.
So with that, let's unpack this a bit.
Yeah, let's do it.
So, starting with a high-level view of the AIX kernel, what can you tell us?
Well, at its foundation, the AIX kernel provides a set of those essential services
Yeah.
that kernel extensions are going to need to actually do their work.
Okay.
But what's really interesting about the AIX kernel is that it's not this sort of monolithic thing.
Okay.
Kernel extensions can actually contribute by exporting new kernel services themselves.
So it's like a fundamentally extendable design.
Precisely.
What are the implications of that?
Well, this means the operating system can adapt and incorporate new functionality without needing to modify the core kernel itself.
And that really speaks to its longevity and adaptability.
Mm-hmm.
So, when a new kernel extension is loaded, maybe you're using the sysconfig command or the modload subroutine, any symbols that it exports, and importantly, any new system calls that it defines become available.
Okay.
Not just to other kernel extensions that are loaded later, but also to user programs and shared objects as well.
Oh, wow.
So it's a very dynamic way to evolve the system.
Yeah, that makes a lot of sense.
Yeah.
It's like having a core set of tools, and then you can, as needed,
Right.
expand that with specialized modules.
Exactly.
Okay, cool. So let's talk about how the kernel actually gets things done, processes and threads within the kernel itself.
Right. So the fundamental unit of execution within the AIX kernel is the kernel process. You'll often hear this called the kproc.
At kproc. Okay.
And it's important to distinguish these from the user processes that you're probably more used to in your development work.
Gotcha. So what are the key differences that a developer should be aware of?
Well, firstly, kprocs are created using specific kernel services. You have the cretap and init services for that.
Okay.
But more significantly, they operate exclusively within the kernel protection domain. You can think of this as having the highest security clearance within the system. They have full privileges.
Full privileges within the kernel. That sounds powerful.
They are.
Are there any particular considerations that someone working with or around the kernel needs to be aware of?
Absolutely.
Hmm.
While those full privileges let them perform those critical system tasks, it also means that any errors or vulnerabilities in a kproc can have really significant consequences for the entire system's stability.
Yeah, that makes sense.
So as kernel developer, it's your responsibility to ensure the robustness and the security of your code.
Right.
Additionally, kprocs can call a restricted set of system calls. We'll talk about those a little bit later.
Okay.
And they have access to pretty much all other kernel services. This is unlike user processes which operate in a much more restricted environment for security reasons.
Yeah, I was going to ask about that. So you've got these user processes, they have limited access,
Wow.
and then the kprocs have almost unfettered access within the kernel's own space.
Right.
What about when the kernel needs to interact with data that's in user space?
Right.
Are there any special considerations there?
Yes. Even with their high level of privilege, kprocs don't have this carte blanche access to user mode data. There are specific kernel services designed for that purpose, and they come with important safeguards.
Mm-hmm.
So take, for example, the word service. This allows you to store a word in user memory. Or the few byte service, which can fetch a byte from user memory. These can only be invoked within the process context of the user process that actually owns that data. So
Oh,
it's a critical aspect of maintaining that separation and protection between the kernel and user space.
that makes a lot of sense. It's like even the kernel has to knock before it goes into a user process's memory space.
Right.
Now, beyond these sort of, I don't know if heavyweight is the right word, but these kprocs, AIX also supports kernel-only threads within these processes, right?
That's right. These kernel-only threads are created using the thread create kernel service. And when a new kernel thread is created, its initial state is TSIDL, that's thread state idle, meaning it's not immediately ready to execute.
Okay.
To actually start running, you have to explicitly call another kernel service called kthreadStart.
Gotcha. So it's a two-step process.
Exactly. You create the thread, and then you explicitly start it running.
Got it. So
Right.
kprocs are the fundamental building blocks for execution within the kernel.
Right.
And they can contain these lighter weight kernel threads that need a separate signal to start running.
That's right.
Okay, cool. So let's switch gears a bit and talk about how user applications actually request services from this powerful kernel, the system call flow.
Okay. So a system call is the mechanism by which a user application can ask the kernel to do a privileged operation.
Right.
It's a controlled and secure way for user-level code to access kernel functionality.
Gotcha.
And as our sources point out, the ability to add new system calls through kernel extensions is a key part of AIX's extensibility.
Yeah, okay. So when a user application makes a system call, what's happening behind the scenes in the kernel?
Well, it's fascinating how the processor actually handles exceptions that might occur during the execution of a system call.
Okay.
From the perspective of the thread making the call, these exceptions are treated as synchronous interrupts.
Synchronous meaning that the exception directly impacts and halts the thread that initiated the system call.
Exactly. The default behavior of the kernel's exception handler in these cases is either to generate a signal that gets sent back to the user process, that's if the process is in a state to receive signals right away,
Okay.
or in more serious cases, to trigger a system dump,
Okay.
which is basically a snapshot of the system's memory at that point in time for debugging purposes.
So a system dump sounds like a pretty serious event.
It can be.
Is
Yeah.
there any way for a program to have more control over how exceptions are handled during a system call?
There is. The setJPX kernel service provides a way for you to do alternative exception handling.
Okay.
It lets a program define a specific point in its code where execution should return if an exception does occur during a subsequent system call.
Okay.
So you can use this to implement more sophisticated error recovery mechanisms within the kernel system call processing.
Interesting. So it's like setting up a designated fallback point within the kernel's execution path.
Right.
Okay. So now when data needs to be exchanged between a user application and the kernel during a system call,
Right.
how's that managed? Especially considering that applications could be 32-bit or 64-bit?
Yeah, that's a good point. That's where kernel services like copying come in.
Okay.
So the kernel has to handle potential differences in data structures between the user application and itself,
Right.
including variations between 32-bit and 64-bit applications. The system call code, as our sources indicate, might use a function like is64u to determine if it's interacting with a 64-bit user process. Based on that, you would then use copying to transfer the correct amount of data from the user-provided memory address into a kernel local data structure.
Okay.
This ensures the kernel can correctly interpret the data regardless of the application's architecture, and also prevents any direct, potentially unsafe access to user memory.
Gotcha. So copying is acting as kind of a secure bridge for transferring that data.
Exactly.
It handles all those complexities of the different data layouts.
Right.
Okay. So now let's move on to some of the tools used to manage and configure the AIX system.
Right.
I've heard about this thing called SMIT. What role does it play in the context of the kernel?
So the System Management Interface tool, SMIT, is a really powerful administrative tool in AIX. It gives you a user-friendly and often a menu-driven interface for managing a lot of different aspects of the system. And when it comes to the kernel, SMIT acts as a higher-level interface that uses underlying commands to actually interact with kernel functionalities.
So can you give me an example of how a developer or administrator might use SMIT to interact with kernel-related functions?
Sure. One example that we can see in our sources is initiating a system dump.
Okay.
Now, you could execute the system start command directly,
Okay.
but SMIT provides a much more guided interface for you to actually configure and trigger that operation.
Oh.
Now, it's important to note, as the documentation emphasizes, that actions like starting a system dump through SMIT They typically require root user authority because you're dealing with privileged system-level operations.
Okay. So SMIT provides a more accessible way to manage certain kernel-related tasks, but all those underlying security permissions, they still apply.
Exactly.
Okay. So let's talk about what sounds like kind of the central configuration repository for AIX, the Object Data Manager, or ODM.
Right. So the ODM is essentially a centralized database that stores tons of configuration information about the AIX system.
Okay.
It keeps track of all the different types of hardware that the system could potentially use, as well as the specific devices that are currently configured and active on your particular system.
So it's like a comprehensive inventory and blueprint for the system's hardware and software components.
Yeah, that's a great way to think about it.
Okay.
Our sources highlight two main databases within the ODM. First, you have what's called the predefined database.
Okay.
And this contains detailed information about every type of device that AIX knows how to support.
Okay.
You can think of it as like a big catalog of all the potential hardware options.
Gotcha. And then the second database.
The second one is the customized database.
Okay.
And this one describes all the specific device instances that are currently defined and configured for use on your system.
Yeah.
These are the actual hardware components or software entities that AIX is actually set up to work with.
Okay.
And for a device to be actively used by the system, it needs to have a complete and accurate entry in this customized database.
So it needs to be defined in the ODM to be operational.
Exactly.
What kind of information is stored in that definition?
So for a device to reach that defined state in the ODM's customized database, its entry needs a comprehensive description.
Okay.
This includes things like its logical name, its current status, whether it's defined, available, and so on. Its change status, which indicates if it's missing, for example.
Okay.
The name of its device driver instance, we often see that as DDINS.
Okay.
Its physical location code, the logical name of its parent device if it has one, and the specific connection location on that parent.
Okay.
It also includes the major and minor numbers, which the kernel uses to identify the device, as well as the names of the methods, which are really executable scripts
Right.
associated with managing the device and its specific attributes.
So a lot of interconnected information.
Absolutely.
So who's responsible for taking all this information in the ODM and actually configuring the devices?
So that's the job of the configuration manager. It's a critical system component that runs during the system boot process. It reads the configuration information from the ODM and basically orchestrates the process of bringing devices online and making them available for use. Now, the boot process actually has two main configuration phases, and the configuration manager gets invoked in both.
Two phases. So what's the distinction between phase 1 and phase 2 configurations?
So in phase 1, the configuration manager is called with a specific directive to configure the base devices.
Okay.
These are those absolutely essential hardware components that are needed for the system to even access the root file system,
Gotcha.
like the primary disk controller, for example.
Okay.
In phase 2, the configuration manager is invoked again, this time to configure the remaining devices in the system, relying on those base devices that were brought online during phase 1.
So it's a carefully orchestrated, staged process.
Exactly.
Make sure that the fundamental hardware is up and running
Right.
before we try to bring up everything else.
Exactly.
Okay, cool. So what about when a device needs to interact with the system bus? Like to get resources allocated, like memory addresses or interrupt lines?
Right, so that's where the bus resolve subroutine comes into play.
Okay.
Device configuration methods use this subroutine to make sure that the device's required bus resources are correctly allocated, especially when you're configuring devices dynamically at runtime.
Right.
We're talking about things like memory addresses, interrupt request lines, or I/O port addresses.
Yeah.
So bus resolve interacts with the customized device's object class in the ODM to check for and resolve any potential resource conflicts with devices that are already active in the system.
So bus resolve is kind of a critical component for preventing those hardware level conflicts.
Absolutely, yeah.
So you mentioned earlier some of the various descriptors that are within that customized devices object class.
Right.
Can you go over some of those key ones again that bus resolve and other system components might rely on?
Sure. So some of the key descriptors include the device's logical name, so we can identify it, its operational status, the change status, to indicate if the device's presence has changed.
Okay.
The DDINS, which points to the device driver, the physical location code, the parent device's logical name if it has one, and the conware attribute, which specifies the connection point on the parent.
Okay.
So all of these attributes together give you a comprehensive picture of each configured device.
Gotcha. Now, you also mentioned major and minor device numbers earlier, which is how the kernel identifies devices.
Yeah.
How are those managed in relation to the ODM?
So the gen major and gen minor subroutines are the
Mhm.
primary tools for managing these important numbers.
Right.
Gen major is used to obtain an available major number for a device driver. The major number identifies the driver itself.
Okay.
Then gen minor is used to allocate minor numbers, which uniquely identify specific instances of a device that are handled by that driver.
Okay.
Gen minor can find the smallest unused minor number, try to allocate a preferred one if it's available, or even allocate a whole range of minor numbers for a single device if needed. And the ODM stores those assigned major and minor numbers as attributes of the device in the customized devices object class.
Now, what happens in the ODM when a device is no longer needed?
Right.
It needs to be removed from the system's configuration.
So the undefined method, which is part of the device's management scripts, handles this process.
Okay.
It first checks if any other devices depend on the one that you're trying to undefine.
Okay.
If there are dependencies, then the undefined operation will usually fail to prevent you from breaking the configuration.
Right.
If there are no dependencies, then the undefined method goes ahead and deletes the special files in the dev directory that applications use to interact with the device.
Right.
Finally, it releases any major and minor device numbers that were assigned to the device, making them available for reuse by other devices in the future. This is done using routines like rel-devno for minor numbers and rel-major if all the minor numbers for a given major have been released.
So the ODM isn't just about defining devices, it's about managing their entire life cycle within the system. Seems like a really central and critical component of AIX.
It is.
Are there any specific object classes within the ODM that developers might find particularly relevant?
Yes, there are a few key ones. So we have PDAT, that stands for Predefined Attribute Table. It contains information about the attributes of all the known device types.
Mm-hmm.
Then there's configurals, which defines the rules the configuration manager follows during those different boot phases.
Okay.
We already talked about CDEF, the customized devices object class, representing the devices currently configured on the system. QDEP stores information about the customized dependencies between devices.
Right.
QDEF holds the customized attributes for specific device instances. CUDVDoctor contains information about the customized device drivers. And finally, KDPD stores the customized vital product data, which is often hardware-specific information.
Okay.
So understanding these object classes can be really helpful when you're developing device drivers or troubleshooting configuration issues.
Yeah, that's a useful overview of those key ODM components.
Yeah.
Now let's circle back to kernel extensions a bit.
Okay.
We know they can add system calls, but what are some other key aspects of how they function within the AIX kernel?
Right. So kernel extensions are, as we've said, a primary mechanism for extending the base kernel's functionality. Beyond adding system calls, it's important to remember that kernel processes, or kprocs, are those fundamental execution units within a kernel extension.
Right.
A single kernel extension might contain one or more kprocs dedicated to doing the tasks provided by that extension.
And what are some of the, I guess, broad categories of services that those kernel extensions might utilize from the underlying AIX kernel?
So our source material outlines a really comprehensive set of kernel services. You have things like services for performing I/O operations,
Okay.
managing the block I/O buffer cache for efficient disk access, handling hardware and software interrupts, facilitating DMA transfers between devices and memory,
Right.
and, of course, services for managing other kernel extensions and device drivers.
Okay.
You also have locking services to ensure data integrity during those concurrent operations.
Right.
File descriptor management, services for interacting with a logical file system, programmed I/O, fundamental memory management routines, interfaces to the virtual memory manager, message queue services for interprocess communication within the kernel, and a whole host of network-related services.
So it's a pretty extensive list.
It really is, yeah.
Highlights just how much you can do by extending that kernel.
Absolutely.
So one final topic related to kernel extensions I want to touch on is this idea of making them key safe. What does that mean?
Okay, so making a kernel extension key safe is a crucial security practice in AIX.
Okay.
It essentially involves designing and implementing the extension in a way that minimizes its direct access to internal kernel data structures and user space memory addresses.
Okay.
The goal is to create a more isolated and robust environment where a faulty or even malicious kernel extension is less likely to corrupt the entire kernel or compromise user data.
So it's all about containment,
It is.
enhancing that overall security of the system,
Right.
especially given that it has this kind of modular nature.
Exactly.
So what are the general steps involved in actually making a kernel extension key safe?
So it typically starts by selecting an existing kernel key set that provides the necessary level of access for whatever the extension needs to do.
Okay.
Developers might then choose to remove any unnecessary keys from their copy of that key set to further restrict its privileges.
Okay.
The next crucial step is to convert that key set into what's called a hardware key set, which enforces those restrictions at a lower level.
Okay.
And finally, and probably most importantly, protection gates are inserted at essentially all entry points into the kernel extension, except for its initialization routine.
Okay.
These gates act as runtime security checks, ensuring that the extension actually adheres to the defined key-safe principles.
So it's a very deliberate and security-conscious approach to developing those kernel extensions.
Absolutely.
Makes sense that this would be important for maintaining the stability and security of such a powerful and extensible operating system.
Right. It's a foundational principle that contributes so much to the long-term reliability and integrity of AIX.
Absolutely. Well, I think this has been a really comprehensive deep dive into the AIX system architecture,
Yeah.
with a particular focus on the kernel. We've explored those fundamental services that the kernel provides, the distinct characteristics of those kernel processes, the journey of a system call, the administrative functions of SMIT, and of course the central role of the ODM in managing that system configuration.
Right.
And then we touched on, the power and also some of those security considerations surrounding kernel extensions.
Absolutely.
So, as you continue to work with AIX, you should now have a much more solid understanding of these essential components.
Yeah. And we really believe that that foundational knowledge will give you valuable context as you develop and troubleshoot applications on AIX, helping you understand the system's underlying behavior better and make more informed decisions in your work.
Yeah, absolutely. So as you go forth, consider how this modularity with its kernel extensions and its structured configuration management through the ODM, how does that contribute to the overall resilience and adaptability of the operating system?
Right.
What might be some of the benefits or even drawbacks of this approach
Yeah.
compared to more monolithic kernel designs that you might be more familiar with?
That's a good question.
This really is just the beginning of a deeper exploration into the AIX internals.
Absolutely. And the official AIX documentation is an incredibly rich resource.
Yeah.
We encourage you to dive deeper into the specific areas that have sparked your interest today.
Yeah, there's a lot more to uncover there.
For sure.
Well, thanks for joining us on this deep dive.
Yeah, thanks for having me.
Until next time, keep on learning.